In this lecture, we will discuss another interesting quantum transport phenomena, which is called the Aharonov-Bohm effect. We will look into the physical reality of vector potential, how the vector potential will turn up in some kind of measurement, and what is the behavior of electrons in the magnetic field, and how you are going to see the Aharonov-Bohm effect in a measurement. Then other variations of the Aharonov-Bohm effect, the Aharonov-Bohm Spivak effect, electric Aharonov-Bohm effect, and we also will briefly discuss some of the landmark experimental observations of the Aharonov-Bohm effect. So, when we discuss the physical reality of the vector potential, what we meant is how do you observe or feel the vector potential physically or in some kind of measurement. So the classical theory, so classical physics generally deals with fields such as electric field, magnetic field, some kind of force field. For example, in this case, B or electric field A. And the potentials are related to this field by del cross A, the vector potential, and the scalar potential is gradient of this scalar potential is going to give E field. Okay. So the concept of gauge invariance of Maxwell equations is based on the fact or based on the assumption that these potentials are pure mathematical construct. There is not much physical significance. And if you replace A with some other term A prime, which involves gradient of a term psi, so gradient of a term chi, and the scalar potential with some other and with the time derivative of this chi, then the Maxwell equations will remain unaffected, or it will remain same. For example, as far as classical physics is concerned, let's consider an electron which is traveling outside a solenoid which carries a current. The magnetic field is always inside the solenoid and there is no field immediately outside the solenoid. So when you have solenoid, the field inside is constant and it diverges once it reaches the end and goes to infinite, and it comes back like this. So immediately outside the solenoid, it's a field-free region, classically. Okay, an electron which travels in a field-free, magnetic field-free region should not get affected by the field, and that is the classical observation of classical physics, where classical physics considers these electrons as particles, nevertheless to mention. And the classical physics also says that there is some term called vector potential, and the magnetic field through the solenoid is given by the curl of the vector potential. What that means is the solenoid, if it is in the vertical direction along the z-axis, then you have vector potential which is circulating the solenoid. Okay. So outside the solenoid, though the field is 0, but the vector potential need not be 0. Okay. So what you have is a region where the electron is moving through, which will have these lines of vector potential, the curl, around that solenoid. And of course, classical physics doesn't talk about the vector potential when you discuss the equations of motion of electron. The Lorentz force talks only about the B field. It doesn't talk about the A. Okay, if the B is 0, that means force should be 0. The force due to the magnetic field should be 0. And we don't bother about the vector potential there. Okay. But in a landmark paper by Aharonov and Bohm in 1959, it's titled The Significance of Electromagnetic Potentials in Quantum Theory, says that in quantum mechanics, you always deal with the potential, not the field or not the force. So this vector potential and the scalar potential, that should come up in your equations of motion. Okay, that should decide the dynamics. It's not the B field, it's actually the A which is going to decide the dynamics of the system, of the electron. And that is the nutshell story of this paper. And that is the effect that we are going to look into in this lecture. Okay. So, just to get the framework set for this discussion, let's look at the motion of electrons in a magnetic field. Okay. I would say the motion of electron when the vector potential is present, a region. I'm not even bothered about the field now. Okay, I'm bothered about only the vector potential. So the momentum is given by mv. This is the, I would call this as a non-magnetic term, and this is the magnetic term. Okay, mv is the momentum in the absence of magnetic field, and Ea is the contribution from the vector potential. Okay, I'm not saying that there is a field, there is a vector potential. Okay, so the total phase occurred for certain region will have the contribution from the total phase when the electron propagates through a region with the vector potential will have contribution from the geometrical path and also the vector potential. So this phase term you can split into two. One, there is a non-magnetic term and there is a magnetic term. And the phase shift due to the vector potential, let me call that theta A, delta theta A, that is given by E by h bar into A dot dl, where A is a vector potential and L is the path. It's a dot product. Okay. So with this premise, let us discuss the picture, the motion of electron shown in this picture here. Okay. What we have is, you have a conductor which is in the form of a ring, and the center of the conductor, there is no, this conductor is in the shape of a ring, and there is a field inside the ring, but there is no field along this path. Field is present only here. Okay. And how you apply field only that in that region, those are all technical details, which we will see how it's done when we discuss the experimental results. Okay. And you also can convince yourself, right, it doesn't really matter if, even if there is field here, it's not going to matter very much. Okay, because the effect of vector potential, the curl of the vector potential and effect of B field are slightly different on the motion. Okay, you can separate it out in an experiment. Okay. Now what I have is I have a conductor which now splits into two paths, okay, and it joins back at another junction J2. J1 splits and J2, and there are two paths L1 and L2 that you can take, that the electrons can take to reach J2 from J1. And the experiment here is you're going to apply flow a current here. You will actually measure the current which is coming out of this region. That is the experiment. Okay. Now we had discussed that this happens when the electrons propagate through this ring as waves. What that means is the quantum nature of electrons need to be preserved. Okay, so you can think this picture as a interference experiment where the electrons will split into two paths and they will join back. So psi1 here correspond to the wave function of the electron which goes around the path L1, and psi2 here correspond to wave function which goes around the path L2. Okay, so now the phase difference accumulated between J1 and J2, or when you start from J1 and reach J2, is basically given by the difference of the phase k into x1 minus x2. Okay. So, and now also remember that this wave functions adds and the current is given by the intensity or the square of the wave function at J2, the total wave function. So this is basically psi1 plus psi2 squared. When you do that, you are going to get a term, a cross term, which is basically a cosine term into delta theta. Okay, some kind of phase difference between the two paths. This is very similar to a Young's double slit experiment where you have two slits and the beam basically adds up on the screen, and the intensity is basically the square of the square of the sum of the amplitudes. Okay? That is what it is. Now, if you assume that the path are equal, the path lengths are equal, that means this is a perfectly symmetric ring. So path length of L1 and path length of L2 are same. Then the non-magnetic term will be same for both. Whatever the phase it has been accumulated over this and this will be same because they are traveling the same length. Okay. Now, but the magnetic term, the arrow dl term will be different because the vector potential changes sign, because the arrow dl will change sign. In one way, the propagation and the vector potential are in the same direction. In other half, for example, this half, if propagation here, if it is counterclockwise direction, the vector potential is in the clockwise direction. So they are different. Okay. So vector potential is a curve. So half of the circle it is parallel to the path, other half is anti-parallel to path. That means you have theta A2 and theta A1. There is a sign change. They are of the same magnitude, but the sign is different. What that means, the delta theta A, which correspond to the phase accumulated because of the vector potential, is given by A dot dl for the full path. Okay, because the sign change, you can consider it's a full path. Okay, that you can convert that into surface integral del cross A, but del cross A will be B dot S. Okay, and of course B is perpendicular plane, and what that means, B dot S is BS, okay, EH bar B as. So that is 2 pi into 5 by phi 0, because phi 0 is the magnetic field flux quantum. So the flux, the phase accumulated because of the magnetic flux enclosed is 2 pi into 5 by phi 0 by an electron in a closed path. Or if you split the path, the phase difference will be 2 pi into 5 by phi 0. That is the take-home message. Okay. Now let us see how would you observe this in transport. Okay, as I told, this is like a Young's double slit experiment, where you have electrons arriving by this path and this path, they interfere at this point. Okay, and if the quantum nature is preserved, the phase is preserved, then the phase difference will be preserved when it reaches here. What that means is the current which is going to oscillate in phi 0. That means there is a cos 2 pi 5 by phi 0 term when you work out the phase difference in the previous slide. Okay. Now what that means is the current is going to oscillate as a function of magnetic field, because magnetic field is the one which is going to change the phase here, because you know that the delta theta A is a function of the magnetic field, or it's a function of the magnetic field or the flux. So when you vary the magnetic field, you're going to vary the flux. Magnetic field and the phase are linearly dependent. So when you vary the magnetic field or when you vary the flux, you are going to find an oscillation in the transmission through the system with the period phi 0. Okay. This phi 0 is a very, very small quantity if you look at the dimension. Okay. So you're going to find rapid oscillations, okay, in the current through the system. Now with the period phi 0. So the center will be maximum when the two paths phase difference is 0. Then when the phase difference grows, they go out of phase, they distinctly interfere, then again 2 pi will come back, and again, so as long as phi by phi 0 is this term, phi by phi 0 is n, an integer, you will get peaks. Okay, that's what it's going to be. Okay, 2 pi, 3 pi, and so on. Okay, so n into 2 pi. Okay, so what you are going to see is oscillations in the current, in the transmission, and that is because of the interference of the electrons propagating through both arms, whose phase difference is varied by the field. Now this is kind of a ghost effect, because the electrons see only the vector potential, it doesn't see the field. Okay, so classically speaking, it's a ghost effect, because there is nothing happening there. Field is varied somewhere in the middle, but electrons are not traveling in the region where the field is present. It's traveling in the region where the vector potential is present, which classically it should not do anything. It's a purely quantum mechanical effect. Now you can also say that for equal paths, okay, to get a peak in the middle, the path should be equal for both arms. Okay, path length should be equal, but path length equal means they should be equal with an accuracy of half of the wavelength, Fermi wavelength, because all the transmission happens at the Fermi surface. So the Fermi wavelength is the de Broglie wavelength. So the transmission need to happen, or the transmission during transmission, electron should not find any path difference between the two arms. So that means the length of two arms should be accurate within lambda by 4, lambda f by 2, the Fermi wavelength. Okay, but that is practically not really easy. So especially in metals, where these are really like, fraction of a nanometer. Okay, and even some of the semiconductors also, it is not easy. So you always will have an offset, a reminiscent, even in the absence of the B field, you always will have a reminiscent phase difference. So the effect of that is like you're shifting you will see a shift in the fringe pattern. Okay, so you will not have a maximum at zero field because you already have a path difference and a phase difference accumulated when it travels through system because of the different lengths of the path. What that means is you will already have a destructive interference happening. So you will not have a peak. But of course, that is not the point here. The point here is you will see an oscillation. The Aharonov-Bohm effect is oscillation of the current as a function of magnetic field. Okay, in a ring-shaped conductor. That is what Aharonov-Bohm effect is. Okay. Now, this is in a nutshell, this is the physics of Aharonov-Bohm effect. Now, let us look at a slight variation of this effect with the same structure. Instead of the current going from the junction J1, this is J1, this junction is J2, you can also have a deflection. You can come back through the ring. That possibility is always there. It's a substantial possibility for that also. What that means, you have now one path going this way, and you can also have another reflection coming this way. These two paths can actually interfere. Okay, so the non-magnetic phase, whether you go this direction or this direction, is same, but the magnetic phase will be different for these two paths. Again, for the same reason of the direction of propagation versus the vector potential. Okay, so you have 2 pi by 5 by phi 0 in one case, and you have 2 pi phi minus phi 0 in another case. Okay, for these two paths. What that means is, for the reflected wave, you can have two of these reflected wave. They can interfere in the reflected direction. Okay, in this backscattering. That will have a periodicity which is defined by the phase difference of these two, that is 4 pi into 5 by 5 0. Instead of 2 pi, now you have 4 pi. That means, in this case, you will find oscillations in the reflected current, okay, IR say, but that also will vary with the field phi, but in this case, the period will be phi 0 by 2, given by this condition, okay, or this condition. Okay, so this coherent backscattering will modulate the resistance with a periodicity phi 0 by 2, not phi 0. This effect is called Aharonov-Bohm Spivak, or AIS oscillation, or AIS effect. Okay, so this AIS effect and Aharonov-Bohm effect, they are actually the same side. There is one side of the two sides of the same coin. You will get both together because you always have a backscattering in the system. Question is what amount of backscattering and how easy to observe that all depends upon the details of the system or details of the device. Okay. Now, there is another twin effect. It's called electric AB effect. So what you had so far is the magnetic field or magnetic AB effect because of the vector potential. But now you can have the effect of scalar potential also. Okay. So here let's consider there is a device with two arms. this is a conceptual representation, but you will see very soon that physical realization of this device is not really easy. It's not that easy. Okay, so you have two paths. They are consider two cylinders where the electric field inside is 0, but they are biased at, these two cylinders are biased at certain potential, V1 and V2. So the potential difference between these two paths is V is given by V1 minus V2. So the electron wave function is given by exponential Et by h bar time dependence, where E is the energy. And since you have potential difference, that also will get added to the energy. Okay, you can consider E is E plus QV by h bar. Okay, Q into V is the charge into potential difference. So now you have your normal path length or phase difference or path difference between the two. On top of that, you also have the electric AB phase, that is given by Q V T by h bar, where V is the potential difference. Okay. Now, as a function of time, you can get oscillations in the current, or if you are varying the potential, then also you can get an oscillation, because all you have to do is you have to vary this term. Okay, vary this term either V or T. Okay, when you vary this term, you are going to get an oscillation. You are varying this phase difference. Okay, when you vary the phase difference between the two arms, you are going to vary the current, output current to this device. Okay, you have junction J1 and junction J2. So when the current flows from J1 to J2, you are going to get an oscillation. Again, as a function of the potential difference, V1 minus V2. And this is the electric field or electric AB effect. All right. Now, let us discuss briefly some of the landmark experiments in this field on this effect. Okay. So far we looked at the physics or the theory of this Aharonov-Bohm effect. Now let's look at the experiments. Okay. So remember, 1959 is what it was predicted, and 1960 was the first experimental observation in a very interesting experiment. It's called biprism experiment. Okay, so it is done in a modified electron microscope, where you have an electron beam or source of electron beam, a very small source. Okay, and this is your imaging plane or a target, and you have something like a biprism in an optics experiment as shown here, where the beam will be split into two and will come back again. So you are creating two arms. Okay, the two paths, these two paths. Okay, now this biprism for these electrons are created by a aluminized quartz fiber, that is F here in the center, and two electrodes E and E. Okay, so the beam is focused between these two, the gaps, and then combine back. Okay, now for an Aharonov-Bohm experiment, you actually need a solenoid. Okay, because you need a field at the center, but electrons are going through a region where there is no field around the solenoid. But remember, this coherence length for these electrons are so small. Okay, and the source size is also small. To have a good coherent source, you need to keep the source size small. But when the source size is small, then you don't have much space to put a solenoid or anything there. But what I'm trying to say, you need something like a fraction of a micrometer, like a micrometer scale solenoid. It's very hard to make. So, but the solenoid is not the necessity. The necessity is the presence of a magnetic field there. Somehow you need to put a field region in the center, but electrons are not going through that field. But you have to make sure that there is a field. Okay. So what they have done is they did an iron whisker of 1 micrometer wide and a long 1 micrometer, thick iron whisker. Okay, it's actually ferromagnetic material which will act as a solenoid. Okay, and also they positioned this whisker in the shadow of this fiber F, so that the electron doesn't see that, electron doesn't go through that or near that. Okay. Now you have regions here where the electrons are going through, which doesn't have any field, which only has vector potential. Okay. Now your aim is to observe a fringe shift with and without the field. You are going to get a fringe because of the two paths. Okay, you will get a fringe anyway. So now, when you introduce an extra phase difference, then there should be a shift in the fringe. Just like in the Young's double slit experiment, think that you are going to put an extra phase difference by putting some dielectric medium in front of one of the slit. Then the whole fringe will shift in one direction, either up or down. That is function of the phase difference. And that's what they observed in this experiment. It's a Denmark experiment. It's a very interesting experiment. The reference is here. But that is the first observation, immediately within a year of its prediction. Okay. And here, in 1985, it was observed in a gold ring, where you have a ring-shaped gold conductor. Okay. And you have the Aharonov-Bohm oscillations in the current measured. Okay. And this is the Fourier transform spectrum, or 1 by delta H. This is in field. You can get two peaks. You will get a peak for H by E and H by 2E periodicity, because remember this is a ring, so you always have a backscattering also. You will have both the Aharonov-Bohm effect and the Spivak effect also. Okay, you have both effect, right? You have AIS effect and you also have AB effect. Both are there. Okay, so you will get peaks corresponding to both in the Fourier transform. Okay. So this is an experiment where the Aharonov-Bohm effect was observed in a metallic sample. And later, more interestingly, the Aharonov-Bohm effect was observed in various other systems, wherever you have phase cohorts. This is in carbon nanotube. You can think carbon nanotube, the electrons can take two paths, this way or this way. They both can interfere as a function, and as a function of the field along the axis, you can actually have a phase difference between these two paths. Okay. Now in this picture you have a carbon nanotube, and this is a cartoon where you are going to measure the current along the tube. You can have two spiraling paths, clockwise and anti-clockwise, and they can interfere, and you get a fringe. And you can change the phase difference between those two paths by varying the field along the axis. And that's what this is. You can see the oscillation as a function of B field. But one interesting difference here is from the Aharonov-Bohm effect in other systems, which we will discuss very soon, is this requires really high field. Because remember, the oscillations are in the magnetic flux, not in the field. what I'm trying to say is the 5 by 50 term into 2 pi, right? Oscillations are caused by this phase. Phi is basically area into the B field. But carbon nanotubes are in nanometer scale, so you need a really high field to get the required flux through it. So, but as opposed to if you have a large ring, then you don't need such a high field strength to get the required flux to observe this oscillation, flux through the loop to observe this oscillation. All right. So when you do this experiment with smaller and smaller samples, then you need a really high field to observe this effect. These oscillations directly you can calculate from the spacing of the oscillation, you can directly calculate the area, because the B, you know the B field, the strength of the B field. Then you can calculate the area, because the oscillations are always in phi 0. Okay, so you can back calculate the diameter of your nanotube from this Aharonov-Bohm oscillation period. Okay, and these are two classic experiments where these Aharonov-Bohm oscillations are observed in gallium arsenide, one of the perfect two-dimensional systems. Okay, where you have a ring-shaped conductor and you are observing the oscillations, Aharonov-Bohm oscillations, okay, in the system. And this is the Fourier transform, which shows both the h by 2e and h by e periods. Okay, this happened in 1988, and this is another example where you are seeing the Aharonov-Bohm oscillations. Okay, in the conductivity. Okay, here it is in the resistance. Okay, and here also you can see the periodic oscillations with period h by e. This is done at a temperature 0.32 Kelvin, fraction of a Kelvin, and this is the device picture here where you have a ring-shaped conductor. Okay, now one interesting note in this case is the temperature dependence of these Aharonov-Bohm oscillations. Okay, so you can see that as the temperature is increased, the oscillations get weaker and weaker and weaker, because you are losing the coherence between the two parts, and eventually it will get destroyed when you reach higher temperature, which is, of course, it's nice to see, but that is, if you think through, that is a natural effect, because as you increase temperature, your scattering events will increase. You can have inelastic scattering events with the phonons, and you will lose the phase coherence, and you will get this oscillations weaker. It's not the period which is changing here. Period should be same, because period is h by e, but what is changing is the strength of this oscillation, the height of this oscillation, which is the strength of this oscillation, the difference between the minima and maxima, that is going to decrease. Okay, that is the visibility oscillations are going to decrease. Okay, because of the lack of coherence, lack of phase coherence. Okay, and that is what you're observing here. Okay, that is also it is also very satisfying to see that the temperature dependence has a role, because that directly tells that when you raise the temperature, you lose the coherence, and that is the base of all this extra effect. Okay, interesting effect. Now, another landmark paper, in this paper they have observed the Aharonov-Bohm oscillation in a quantum Hall system, where you are seeing the Aharonov-Bohm effect because of the interference of the edge states in a quantum Hall system. So you have a ring shaped region in the center, which is an antidot, and you have two gates. So what you are going to get is, when you have such a geometry, you are going to have, in the quantum Hall regime, you are going to have edge channels which is going around like this. These are edges, as we discussed in the quantum Hall effect lectures. You can have tunneling to this edge through this antidot, and you can have tunneling back. So what you are going to have, you have a ring-shaped region here, and the edge channels are going to propagate along that. So when you measure the current between any of these edges, as a function of magnetic field, it is going to have interference effects on the plateaus. And of course, the period is a function of the electronic or the charge of the quasi-particle. So in this case, this corresponds to the integer quantum Hall plateau, whereas this one corresponds to the fractional quantum Hall plateau, where you can see that the period is very different, because it should be a function of the effective charge of the quasi-particle, which is not a part of the discussion, but it is actually it's a very interesting and landmark experiment where you can directly observe the fractionally charged quantum Hall quasi-particle using the Aharonov-Bohm interferometer. Okay, so to put in a nutshell, what we have discussed in this lecture is the basics of Aharonov-Bohm effect, the interference of electron to interference of electron, and the effect of a magnetic vector potential, not the field, okay, magnetic vector potential on the phase difference. And it's a purely quantum mechanical effect. This is going to give you oscillations in the current through the system, which is in the shape of a ring, as shown here or as shown here. Okay, and the period of this oscillation is phi 0, or you can also have phi 0 by 2, depending upon whether it's a backscattered interference or it's a interference between two forward propagating paths. You can also have interference of quasi-particle in quantum Hall systems, where the charge state is something different. The charge of the charge state of the charge carrier is something different from E. Then the period is going to vary accordingly. Okay, and you can also have similar effect with Cooper pairs that we will discuss when we discuss mesoscopic superconductivity.